This example asks us to find the area of the part of the plane 2x plus 5y plus z equals 10 that lies inside the cylinder x squared plus y squared equals 9. So we have a surface whose area we were trying to find. We recall the surface area formula. There are several different ways of writing it. I'll do it this way here. We'll say that the double integral over the domain D of the square root of, we'll take the partial of z by x squared plus the partial of z by y squared plus 1 dA. You note the similarities to Pythagorean theorem here, and the similar structure to probably the first arc length formula you learned in Calc 2. So this tells us what we need to compute. We need to figure out what our domain is. Well, that's described as being inside the cylinder x squared plus y squared equals 9. That gives us a disk in the xy plane. So we know what that's going to be, a disk of radius 3 centered on the origin. So we're fine there. We need to compute the partial of z by x and the partial of z by y. And for that, we want to write z in the form of a function of x and y. In this case, z is fairly easy to isolate. That is 10 minus 2x minus 5y. The other version of this surface area formula, of course, has f sub x and f sub y, which would assume that you have the function written as f. For these purposes, z and f are going to be equal. So whichever form you're given and whichever form you prefer to use, you may need to adapt one to the other. So we need to find some partials. And actually, these are easy enough to do. I suppose we can just sort of dive right into this, can't we? So S would be the double integral over the disk D of the square root of the partial of z by x. Looking at that, that looks like negative 2 squared, plus the square of the partial of z by y. That looks like negative 5, plus 1 dA. Let's start cleaning this up a little bit. We see that this is a constant here. We have 2 squared is 4, 5 squared is 25. So if 25 plus 4 plus 1 is 30, that is a constant square root of 30 that we can pull out of the integral, like so. Now this cylinder that we have is perhaps best described in polar, but we don't really need to do that, do we? Because if we look at this integral, this is the double integral over the domain D, dA. D, again, is just a disk of radius 3. The double integral of that dA is simply the area of the domain, isn't it? This domain is a circle of radius 3, that is pi times 3 squared, and it looks like we get 9 pi radical 30. So this is actually a much simpler example than it appears. The first part is simply showing the basics of how we adapt what we're given and fit it into the surface area formula, so we can use that. The other point here is that as things simplify, if you ever find yourself integrating 1 over an interval or a domain, or pretty soon here a volume, so a dA or a dV or whatever, if you think about what that means, that's just accumulating whatever content you have there, right? If you have a single integral times an ordinary differential, or of an ordinary differential like dx or dy, that's just the length of the interval. When we have a double integral of a domain, dA, that's just the area of that domain. In upcoming sections, we'll be looking at triple integrals over some domain dv, that's just the volume of that domain. And if the domain has a shape that you can easily find the area of, you can just use that fact. Unless, of course, that's the question you were asked to do, right? If you're asked to find the area of such and such, it's understood in this context that we want you to go through double integrals, But if that's not the point, if we are clearly doing something else here, and it's just, okay, now finish up and figure out what you need, if you boil this down to an area like this, you can just go ahead and leverage that fact to more quickly compute this. You don't have to, of course. You could do this in polar, right? We could instead have turned this into like the integral from 0 to 2 pi of the integral from 0 to 3 of r dr d theta. And then as you work through that, you have integral of 0 to 2 pi d theta times the integral from 0 to 3 of r dr. And you see what's going on here, right? We get a 2 pi here, and we'll have a 1/2 r squared evaluated from 0 to 3, which gives us a 1/2 3 squared there. 2 and the half cancel. We've got pi times 3 squared. We get the same result over here. But if we use the geometry, we can get there a lot faster. So, that's just sort of an optional approach or technique you can use in some of these problems that happen to simplify more cleanly than we might otherwise expect.